Hey all! In episode 21, we coded the Lorentz attractor, which introduced us to the chaos theory. But no discussion of chaos is complete without plotting the chaos equation. So today let's just do a very short episode and plot the chaos equation onto a canvas. Hey!
Hey,
Ravi, and hey, welcome Divakar.
Hi.
How are you doing?
I'm good, thank you.
Okay, I don't think you're coming on camera,
In
so
camera.
I think if you can just come
Yeah.
in.
scooch in.
Yeah, so we have our friend Divakar joining us today.
Hi.
And so it's just me, Ravi, and Divakar today.
And I can just squeeze in from behind Divakar.
I'll hide you wherever you're going.
Yeah.
So,
yeah.
RK, what's today's plan you were talking about?
The
Chaos
chaos equation.
What is
All
that?
right? Okay, so this is the famous chaos equation. All right.
Okay.
Where you basically have a series, and I think this models population.
Right.
essentially. All right.
Right.
So let's say, typically what we say is that what will be the population next year of a
Right.
bunch of rabbits, given
Rabbit.
that you have certain growing conditions for the rabbit and a certain rate of growth. Or let's
Right.
say certain conditions for the rabbits and certain
Some
growth
rate
factor,
of
some
rate of
growth.
reproduction.
Rate of reproduction.
They keep reproducing rabbits,
Exactly.
and then something that stops them also.
Something that stops them or something that
kills
inhibits that
some rabbits.
some rabbits.
Right.
It could be anything. It could be disease. It
Yeah.
could be predators or anything. But there is like a certain
Constraining factor.
there is a certain constraining factor.
Right.
If the constraining factor is like, for example, 0, then you'll have like an exponential growth.
Right.
So if they have no predators, no no
Disease.
disease, nothing,
Sure.
you will see an exponential growth, or something of that sort.
Right.
And this is the chaos equation. This equation actually holds true in a lot of scenarios. Okay, well, I say scenarios, but what I actually mean is that let me just make sure that I have switched cameras. All
You
right,
didn't.
so I haven't switched cameras. No problem. We can just look at the formula once again. I mean, this is the actual formula that we are talking about, where x of n is equal to r into x of n multiplied by 1 minus x of the of n. So this is actually the constraining factor. R is actually the rate of growth,
Reproduction.
the rate of reproduction, and then the next generation or the number of animals that you'll have in the next generation is depending on on this factor
Right.
over here. So you basically have to do this over and over again for a certain number of generations before this number starts to settle down at one point into this one onto this one number. So I think that's what we want to plot today. All right. And what do I mean by plot? So what I have here is an Excel sheet where I have like a base rate defined. Over here I've defined it as 0.9. I have, like, let's say for example 24 generations, and I have a starting x, right? So the starting x in this case is, let's say, 0.5, and if I plot this onto a chart, this is what it will look like.
Right.
So you will see that that if the rate of multiplication was below 1, if the rate of
Then they are
then
dying.
they would basically essentially die. So you can see
Die.
that by the 13th generation there are no more rabbits left. If I make it as 1, you'll see that it is doing
Surviving a little better.
surviving a little
Longer.
bit better. But eventually, I mean, if you have like more and more generations, over here we are just only counting 24 generations.
Right.
That's not enough. But if you have more and more generations, they will tend towards
Die.
0.
Yes. they are.
So let's say if I make this as 2, you'll see that it sort of remains stable at 0.5,
Okay.
right? And if I have, let's say, 2.5, you'll see that this is what happens to I mean, it stabilizes over
Right,
here. All right.
right.
I mean, you might wonder what this chart is. These both are actually the exact same chart, whereas this one is a line chart. This one doesn't have those lines, but essentially they are the same chart. And I have this for a very specific reason. I just want to show you what I intend to do with this one. All right. Now, there is a magic number 3.2, beyond which what will happen is that the population starts fluctuating. So you can see that there is a split that has happened in this, in this population. And 3.4, for example, you will see that the split is even more pronounced.
Right.
And I think at about 3.6, it splits, I think, into four different. I mean, so the period of this rate I would say is basically 4.
Right.
Now we basically need to plot this, onto, let's say, a canvas or something. So let's say I have, I'll just go back to 3.2 for just a minute, and let's look at this chart. If I was to like squish this in such a way that, the number of points are not visible, then you will see that there are only 2 points that are essentially shown over here. All right. And if I had, let's say, 3.6, then you will see that there are, maybe let's say there are 4 points. I mean, the individual dots are thick, but the point still remains that there are now 4 splits that are happening. So that's 1, 2, 3, and 4. So it starts from 1, 2, 3, and 4. I mean, it sort of has a lot of periodicity into it. Okay. The chaos equation, I'm just going to pull up the very famous chaotic equation image, and this is the image that we intend to see with our,
it was
with our
famous, but I didn't
today.
know it up till
now.
Okay.
So this is the image that we intend to see today. So I'll just make this a little bit big so that you all can see it. So what you see over here is that, I mean, let's say if I have it at 0.9, for example, you will see that the chart goes in this manner, and at 0.9, it will look like this. And at R3 equals to 0, there is supposed to be a split that happens. So that is what happens with the split. You can slowly see that the split has started to happen. And this is what it would look like if they are all squished at the y-axis. Okay. And as you go beyond 3, you will see that more and more splits happen. And so I'm not sure what this is. Okay, let's assume that this is just 3.4 or something, 3.6. I mean, I think that is 3.6. This 3.6 essentially represents the split, the further split into 2. But beyond that, this entire thing becomes chaotic. It becomes chaotic. All right. So I don't want to explain a lot over here. We will draw our chaos chart, and then I'll get on to the explanation as to what's happening. Or at least I'll try to do my best to basically see what's happening. All right. So we begin our program, and looking at the chaos equation, you will see that we will require a rate. And so we will require a rate. So let's just declare the variables required for that. So I'll say rate, and I'll also have a variable called increment rate, which I'll just assign it to 0. Rate, I will assign it to, let's say, max to a value, to an initial value. All right. We started ours with 0.9, I think. Let's just start with 0.4 just to be on the safe side. We can actually start with 0, I think, also. I think it would be great if we can just see what happens if it's 0, it's 0. So I think 0.1 would be like a nice place to start. So I can start with 0.1. Now, all of these chaos, so the rate needs to be incremented, which we will calculate, and basically this chaos equation needs to stop at a specific rate. All right, and we can say, let's just declare a variable called max rate, and I'll say max rate is, let's say, 6, for example, over here. All right. So when this rate reaches the max rate, we will stop plotting the chaos equation. That's the idea over here. Increment rate. All right. So now we have a canvas that is of a specific size. We want to basically plot this rate onto this canvas. So the amount of increment of this rate should be tied to the width of the canvas itself. So that's what I'm going to do.
It can't be 0, right?
I mean, it starts at 0, but then it just needs to be initialized. So what I'm going to do is I'm just going to say increment rate is equal to 1 by width for now. All right, or let's say 5. all right, let's say 4 by width for now, so that the rate of increment itself is very slow, so that our chaos equation looks very granular when we start working with it. Okay, all right, so that's my increment rate, and yeah, so I mean I have it initialized. And when I start to plot this, I also want to make sure that I start from from the bottom left onwards, and then I and then the chaos equation will be sort of plotted along the way. All right. So it does require to be started from a particular place, but you know what? That's fine. Let's give our context a specific. So I'll say this is our context. I have got the context and everything. Let's give it a color. All right. So context dot. What is that? Fill style RGBA. So I'll just say this is. Let's just make it like a nice red color. All right. 255, 120, 120, and for now I'll just say this is 0.5 is the alpha. All right, so that's my fill style. Okay, now that in this equation I have the R, let's also have the X for example over here. Now remember, for each Y position or for each iteration, I'm over here we are calculating 24 generations. All right, so let's just do that. All right, so I need that X, and that X is essentially the generation itself. That's the generation count, or the number of animals in the generation. So I'm going to call it gen count. All right, and what is this gen count in this in this Excel file? It's nothing but this nothing but X over here. That's the gen count, and like it is on the Excel sheet, I'm going to start it with 0.5 for example. I'll say for let I is equal to 0, and we went 24 steps, right? So I less than 24, I plus plus, and all I need to do is basically calculate that, right? So the next value of gen count would be what is that? It is rate into gen count, so that is rate into gen count into 1 minus gen count. You get it, right? So basically that
1 minus rate,
1 minus gen count, yeah, which is 1 minus gen count. All right, so I have that. Now I need to plot all of this onto an X and Y. All right, X is of course wherever the rate is. All right, so the rate of increment would be the X. So I just have to say X is equal to whatever the current rate is divided by the max rate. Okay, I think that will be multiplied by the width. Okay, so that's where the X would lie, and then it would also require a Y. The Y would actually be dependent on the gen count. For now, I'm just going to make it proportional to whatever the value of gen count is, and I'm just going to say gen count by height. And at this specific location, I'm going to draw that. So I'll just say ctx dot fill rect. X comma Y comma 1 comma 1. So this is drawing like a small dot at that X and Y location. All right, and then I have a set timeout which basically has no sleep value, and then it just calls the chaos. So it will just draw this chaos equation as fast as possible. All right, now if I was to execute this, hopefully I have no errors. So the chaos equation is actually drawn, but I don't think it is very thick enough. All right, so essentially what's happening is that this iteration is not deep enough for anything to be plotted. We are only plotting 24 dots, right? So I'm just going to make sure that this is a little bit thick. I'm going to make it 1,000. So this, we will let it go for 1,000 generations. Oh yeah, I mean, of course it won't draw anything. That's number one, because we haven't incremented rate at all. So what we'll do is, where is that? So we'll have to increment rate. So I'll say, rate plus is equal to increment rate, and I'll say if rate becomes greater than the max rate, then I'll say I'm just going to say console.log done, and I'm just going to say return, which means we don't have to do anything after it does this, and hopefully this draws the chaos equation. So you can see that the chaos equation gets drawn, and you can see, you know, how beautiful it has, like, it has drawn it. But it's like, but it's upside down. I mean, basically it's drawn it upside down, and I think we can easily fix that by just saying height minus gen count into height. So it basically is the other way around. Alright, so let's just do that and see what happens. So there you go. So that basically starts the chaos equation, and it basically shows that. Alright, I think the canvas is a little bit tall, so I'm going to make it a little short, and I'll say that the height is only 600, for example. So I'll just leave it like that, and maybe I can increment the width, let's say 900, and see how this goes. Alright, I think, do you agree this looks a little bit better? Right?
Yeah, totally looks like that same image.
Looks like that exact same chaos equation. Alright, so we have this this thing happening. So that basically plots the chaos equation.
Wow.
But if you, but if you recall the image, these lines were actually. So let's just bring up that image once again. And what I want to do is I only want to bring up this image instead of the whole site. Okay. Is it possible for me to do this? No. Okay. Open image in a new tab. Alright. You can see how very well defined these lines are. Right? But in our chaos equation, it looks like this. This is like an easy thing to solve. We can do something like. You saw this one, so we can just say 0.05, for example. Decrease the alpha, and now you can see that it actually plots just the main lines itself.
Nice.
So the ones, I hope it's clear what's happening over here. Those lines are still over there, but they don't get noticed very well because their alpha is like turned down way below. And the reason why only these lines are shown is because there are so many plot points at that, so many results at that specific location that they just become visible as such. All right. So that's plotting the chaos equation. Now, is there any way we can make this better? One thing we can do is maybe we can.
1,000, 5,000.
Instead of 1,000, 5,000. So at each line, it would draw it 5,000 times. So maybe we can increment it by 2 and see what happens. I'm going to set it back to 0.5 because I do want it to be drawn. So at each X location, each slice, it draws it 5,000 times. So you can see the chaos equation being drawn.
You made it 2,000.
Yeah, I made it 2,000. So it draws 2,000 points at each location, and this starts and this stops at 6 over here. So let's say if I was to stop this at 8, I should see some more drawing happening, right?
Yep.
It's become shorter.
Yeah, for some reason, it's become shorter. But it did get. It did get a little bit compressed. Is that what happened? Oh, okay. Yeah. I guess so. So okay. We also had something called as the increment rate, which we did this. I'm going to make this 5, and let's just make this 6, for example. Okay. Yeah. So you can see, and then it basically printed this done out over here. So what can we do to improve this? It's just like a nice plain red color, right? Maybe we can introduce hue to it and then make it a little bit more pleasing to the eye to see. That's number one. Number two, and you can see that the rate actually doesn't increase well into a specific value over here. And I guess that value is 0.9 or 0.5 or whatever. So we can maybe make this rate as 0.9, and you can see that it actually starts from this location, and we want it to start from this place. So maybe we can just use the translate function, and then you can start from the very left hand side of the screen itself. And to do that, we can just say let x is equal to basically whatever we did over here. I never declared these as variables, so I'm just going to declare them. So I'm going to use this, and then I'm going to say context.translate minus x into 0. Okay, so translate will basically translate the screen. So no matter where I start from, it will always start from the bottom left hand corner. Alright, so it will always start over there. Another thing that I can think of is this is rate by max rate into width. Yeah, so that would actually be correct. Oh yeah, I mean this has to be width plus whatever translation that I have done over there, right? So yeah, so maybe I can just declare that as a variable, and I can say let this translate x, and then I can say negative translate x, and over here it would just be width plus translate, right? So that we can just make sure that it isn't squished in the x direction in any way. All right, hopefully that fixes it. Oh no, it actually began from here. So should I say minus or no? No, this is correct. I think we can just leave it like that because that's the overall width of the canvas itself. We can just leave it like that. All right. Another thing that we can do is, I mean, I have this constant fill style. Maybe we can just have a hue. So I'm just going to have a hue here, for example, and let's say hue is equal to 0. And I can say context.fill style is equal to HSL, which is hue, saturation, lightness, plus hue, comma 100% saturation, 50% lightness. So I'll do that, and what I'll do is I'll just say hue, plus equal to something. Plus is equal to 0.03. For now, I'll just leave it like this and see if this hue essentially works. So yeah, so there you go. I mean, it just basically gets to start into that yellow range, which means my hue should be actually very, I mean, I should increment my hue very slowly. So I'll declare a variable for that as well. I can say, I can start it off, initialize it to 0. And I can probably say 1 by width. So that's my increment hue. Okay, and hopefully I get the full spectrum of colors, which it has not. I mean, it still remained as, oh, what did I do?
Can you mix some colors? RGBA?
Yeah, I mean, basically that's exactly what I'm attempting to do. The hue is supposed to essentially do that for me. So I can say hue plus is equal to increment hue. That should actually work for me. Oh wait, how much is, oh okay, it has to be 100. Okay, so the maximum hue that you can go is 360. So I'll just say 360 by width. So I think that should cycle through all of the colors. So there you go. So that's actually one thing that we can do to improve this. Another thing that I can think of is maybe I can just make the background black. So I can say context.fill style is equal to hash 0, and then
what is 000?
Black. I mean, basically it's a hexadecimal number, or a base 16. I mean, each two of, okay, so it's red, green and blue. 2 digits for red, 2 digits for green, and then 2 digits for blue. Each 2 digits is a hexadecimal value between 0 and 255.
Okay.
Yeah, so this is black essentially. When you say everything is 0, it means it's black. And say fill rect 0, 0, width, height, context dot. Oh no, you know what? I just have to do it black once. I don't have to do it with every, I really don't have to do it with each and every loop. So I can just do this once. I mean, I can just paint the background black once and then be done with it. Yeah, so there you go. So that's a more beautiful way of putting the...
Beautiful.
Right? I mean,
Yeah.
it does look very pretty, right? I mean, this chaos equation. There is a translate that's happening, so I'm just going to make sure that the translate... Peacock, yeah. I mean, it's a very pretty way of actually...
Maybe peacock has a significance to chaos.
How's that?
Nice.
Right? Yeah. So, I think one of the things... okay, so I can just say... Okay, so X is rate by max rate into width. Right? I mean, the rate at... So, the rate where it is... And what if I say minus translate X? See what happens. No, I mean, it has to be plus, is it?
This is coming closer to the picture you saw on the Google.
On Google, yes, it does. Yes, it does. Yeah, I mean, basically, it should look like this. I mean, they are starting their R from 2.5. We are starting it at 0.9. Yeah. Yeah, I mean, we are starting it over here at 0.9. We can also start from 2.5. Which is fine. Oh yeah, I mean, I think one thing that you can change is, let's say you can make the gen count as 0.4 and you'll see a much more. Oh yeah, I mean, you can see over here what happens in this chaos.
Also, there's a lot of lines in between that center.
Over where?
These kind of lines.
These kind of lines. Okay.
Which are not there in
Yeah. So I think the one thing that I wanted to talk about in this chaos is that in the chaos equation is that there is stability between between, let's say, 0.9 over here and all the way to 3.2, where it bifurcates.
Correct.
And then there is stability. Basically, you will see that there is absolutely no color over here at all.
Yes.
All right. And then once again, there is stability after a certain point. You will see that there are no caps. And after that is like absolute chaos.
Correct.
Which means that the populations, that the amount of populations after that so many generations is like absolutely chaotic. But every once in a while, there is a stable island that is created. Where over here, for example, if you see this line, I mean, I really hope it comes out really well on the screen. You will see that there is an island of stability over here. So populations are only confined to these locations where color is actually set. And then once again, there is absolute chaos in the number of population. And then there is once again there is stability.
That stability is what he was talking as 3.8 or something, right?
Yes. Yeah.
There's one. Yeah.
Yeah. I mean, maybe on the top over here, I can just show the
R
rate,
also.
the R also, right?
Right.
So I can, so I can do something like this. CTX dot fill text, right? So fill text would be rate dot to fixed of 3. I mean, just 3 decimals followed by, let me just say 10, 10 for now. Oh no, I mean X, I have a translate X, right? So I'll just say translate X plus 10, 10. So I should see, I mean, but you can see, I mean, the font is small, first things first. So I can just set a font. Oh, let's say font is equal to, what is that? I can say 20 pixel mono font, for example. And it should make the font a little bit bigger. I'm just going to increment the Y to, let's say, 20. And I'm also going to clear the rectangle. But I'm only going to clear that part of the rectangle. That's one thing great about the
canvas.
Yeah. Right. I can say clear rect 0, translate X, 0, I can say clear up to 100, 25. Right? Let's see what happens now. So you will see that the number gets printed and then
after 5 it's anyway useless.
It's anyway useless. I mean, but you can see that there is an absolute chaos that happens over here. I mean, you can't see it on the screen, but if you look at the dots over here, so after a certain point, I think this point is 4.7 or something, it becomes absolutely chaotic, which means there is no island of stability after this place at all.
Yeah.
So this equation is actually tied to a lot of real life phenomenon in a lot of real life phenomenon. I mean, one thing that is connected to is the Mandelbrot set. So if I can just if I can just have the Mandelbrot set image just shown up over here. So this part of the Mandelbrot set is actually connected to this part. All right, and then where it bifurcates, this island of stability is connected to this island of stability, and then these bulbs over here that you see is connected to these bulbs. I mean, it appears in the chaos equation at exactly the same place where the bulbs in the Mandelbrot set it arises. All right,
Amazing.
and then you will see that it's a straight line, and then there is a Mandelbrot set over there also. So that actually
is that line.
Is that line over there.
Amazing.
So somehow it's all connected, the
Crazy.
chaos and everything.
Amazing. Yeah.
It's connected. Yeah. I mean, that's all I had to show for this week.
Very cool.
A very simple episode where we can just show the chaos equation being plotted. And like I said, no discussion about chaos is actually complete without plotting the chaos equation and seeing it in real life. So that's all we had to show for this week. Do join us again next week. I hope we have something interesting coming up next week. Thanks for watching. Do like, share, and subscribe. Do share it with your friends.
And check out the code on GitHub.
On GitHub, check out the code on GitHub. We will upload this to our website also, and our website also will have the canvas where you can actually see this play out and things like that.
Very cool.
Very cool. All right.
Ciao.
Yeah. Ciao. Thank you so much.